So I would like to start with a very, very short personal story. So Edinburgh has a special place in our family's hearts. My dad got his PhD in 1949 with Max Born in Edinburgh. And so talk of Edinburgh, Max Born, and quantum mechanics was how we grew up. Grew up with Edinburgh and kind of like a special place and quantum mechanics. And my dad was writing quantum mechanics books when I was born. And I didn't understand then, and I still don't understand. But it's a great motivation to what I want to talk about. So I will start with quantum mechanics. And if you look at quantum mechanics, you see immediately some big mismatches with classical computing. So on the left, you're totally fine writing things like lambda x, xx, that copy x and create two copies of x. In quantum mechanics, there's a theorem that this is impossible. The no-cloning theorem says this is impossible. And conversely, you can also do, you can discard. So here I have A and B, and I have proof that A and B are equal. And I could certainly write a function in any classical language that throws away the B. Again, this is impossible. There's a no deleting theorem that exactly says that if you have two quantum states and they are identical, you cannot get rid of one of them. So there's something fundamental here on the side of classical computing that allows copying and deleting, and quantum mechanics doesn't allow that. On the other hand, quantum mechanics, if you open a textbook, you will find all of these real numbers. And they are computable, so it's fine, but they're not constants. You cannot really assume they have zero cost or constant cost. And so there's something also kind of strange going on with complexity. And that is another mismatch. And same thing, you have sometimes equality on these real numbers. And again, if you have computable reals, I mean, equality is not decidable. So there is, it seems that quantum computing, quantum mechanics assumes infinite precision reals given as constants. And it seems that on the side of classical computing, we can copy, we can delete, we can do things. So there's a mismatch among other things. So what do we do? Oh yeah, so first, the issue of complexity and precision in quantum mechanics was debated quite a bit. I mean, it's not like I just discovered this. I mean, this is well known. The most famous of these arguments was a series of papers that was initiated by this one that essentially picks one of the fundamental theorems of quantum information and says that finite precision measurement nullifies it. And the details are not kind of what we want to talk about today, but there was a series of papers arguing back and forth that no, actually doesn't nullify, and then no, it actually does nullify, and then somebody pointing out that maybe the real numbers are the kind of the catch here. So this debate has been going on, and I just wanted to mention that this is part of the mismatch we have, and that a priori, trying to get classical and quantum mechanics or quantum computing to talk to each other is not going to work. Okay, so there are kind of two things that certainly one can do. You can try to bring each of these close to each other. So on the side of quantum mechanics, you can try to do some kind of finite precision version. And as I've mentioned, some people have been doing this, and we also have work on that, trying to do something based on finite precision, numbers like we do in computer science. Everything is discrete, and we account for the number of bits and precision. And so there's like that work we have done, but that's not today's story. Today's story is about the other side. It's about taking classical computing and try to embrace the idea that there's no cloning and no deleting. So that brings us, again, a step closer to quantum mechanics. It doesn't bring us to quantum computing all the way, but it brings us one step closer. And it turns out you can certainly do classical computing with that model, and that's in, like, broadly speaking, this is the area of reversible computation. In a very broad sense, the idea that you can go back and forth in computation, you do not delete information, not create information, so you can go back and forth when you're computing. And that has been, you know, in software engineering, even people have been arguing that this is a good principle for many of the systems we have. Are you asking a question, Nuhad?
Yes, please. Is that okay?
Yeah, sure.
So there's no guarantee that even, you know, when we embrace reversible computing and no cloning and so on, that we actually will be able to bridge the gap. It's just like a necessary step, right?
Yeah, I mean, yes. So it is, yeah, trying to bring the two things. Let me put it this way. If I wanted to study quantum computing, I mean, I can jump in directly, and maybe that's the picture, maybe that's the answer. This slide is your answer. We have at the bottom, physics has these principles, no cloning or deleting. Then we, over the years, we have built abstractions, computational models, including things like the LAMBDA calculus, other Turing machines, and so on and so forth. And in those models, we allow cloning and deleting. Now, we could maintain the LAMBDA calculus and everything we have done pure science for the last, you know, 80 or whatever years, and try to add a layer on top of that that builds quantum computing on top of it. So we can add linear typing, comonads, add all kinds of, you know, things to try to recover the properties that we want from quantum mechanics. But my idea is, instead of doing this, let's rethink from scratch and let's develop a new calculus that doesn't have this detour. Instead of starting from no cloning and no deleting, allow cloning and deleting, and then try to recover the initial property. And let's just define a calculus from scratch that has no cloning and deleting. That will be a more direct way of trying to get closer to quantum computing. Is that answer the question?
Yes, I'm happy, I think. Thanks.
And certainly, please, you know, if there's any comments or any questions, I mean, I would certainly enjoy having the questions. At least, you know, in a real seminar, you can see people's faces, and now I cannot see anything. So at least getting some feedback or questions would be helpful. Okay. So this is what we are talking about today, this information preserving LAMBDA calculus, if you wish. It's not a LAMBDA calculus, but like a model of computation, simple model of computation that would be information preserving. And so what we're going to start with the first order version, and that's fairly easy. We'll quickly review it. And then we'll notice that this first order version has models in these monoidal categories, which I'll explain. Monoidal categories have extensions to compact closed categories, which are high order. And this is how we get our high order version. So that's the story. We'll start with first order, and then use the constructions from category theory to try to get a higher order version. So we'll start now with the kind of the meat of the construction. Okay, so we are starting with the first order, and I'm using Agda syntax, hoping it's, you know, I mean, I'm trying to explain it. It's hopefully readable, but if there are any questions about the notation, please let me know. So we will start with finite types, the empty type, the unit type, sum types, conventional sum types, and conventional product types. And their interpretation as the empty type and the unit type and disjoint sum and, you know, product are the expected, what we have in any programming language we have. And then, of course, we, as usual, will abbreviate 1 + 1 as bool and have a convention that If you inject left is false, inject right is true, and it will shorten the notation a little bit. Okay, so this is our base type system. And now we would like to do reversible computations between those types. Another name for these reversible computations is type isomorphisms. I mean, we'd like isomorphisms between the types so that we can go back and forth, conserve information. And in this particular case, all you have to maintain is the number of elements is maintained. So if you just count the number of elements, and if you interpret the types as natural numbers, 0, 1, and this as plus and this as times, that gives you the number of elements in the type. And all the isomorphisms will have to preserve the number of elements. So this is fairly well known. Let me give you an example, because this slide is important. It has a lot of stuff, but I'm going to spend some time on it because it would it's not immediately obvious that this language is rich enough to do anything interesting. It's not rich enough, for example, to do conditionals or to do some kind of copy or something like that, but it does. And this particular isomorphism, let me try to scribble here, maybe that's, so this isomorphism here, which is two isomorphisms really, an isomorphism that go from A plus B to C, sorry, a pair of A plus B times C to a sum between AC and BC. And you can go left to right using distribute and right to left using factor. So that isomorphism, that type isomorphism, is crucial to do all kinds of things. You can use it to copy, you can use it to do conditionals. And I'll try to explain that. So, so first, here's a little circuit. It uses distribute and factor. So it has two inputs, two bools. So all of the types here are, so this C is a bool, A and B are 1 and 1, so this is a bool cross bool, so we have two bools. And we distribute, so we get a sum type. On this side, we get a bool times 1, and here a bool times 1. We can negate this bool, so swap changes inject 1 to inject 2, and inject 2 to inject 1, so it maps false to true and true to false. And then we can factor, get back to the product type that we have initially. Okay, so this is a small circuit, and this ends up, if you kind of trace the truth table, you will see that this is the truth table of this circuit. So if the first input, which is red here, is false, then this is false, so you're in the left injection, so you are in the left injection here, which means you're up here, nothing happens, so you return exactly the same input. So F true return the same thing. If the first input is true, you go down here and you swap the second bit, so you do, the second bit is flipped. So this is a conditional operation, because if the first input is false, you do nothing. If the first input is true, you flip the second one. So it allows you to do conditionals already. Another thing it allows you to do, if I can get, yeah, here we go, is if you fix the second input to false, you can see what happens to the first one. If the first one is false, you get to false, false. If the first one is true, you go to true, true. So that copies the first one. So that same circuit is kind of like an amazing thing. It's a conditional operation, it's a copy operation, but a reversible copy, not a copy, because we cannot do like a unrestricted copy. This is a reversible copy. You can always go back to where you came from. And so we have quite a rich already language. And now we can imagine writing actual programs, because we have quite a bit of primitives that we can use to write basic building blocks. Okay, so before I move on, any questions about this? This was like a dense slide. Yes, Phil, go ahead.
Hi, Amr, it's great to see you. I'm confused that you're saying that this is a copy, because it looks more like the identity function, right? A copy, I'd expect two copies of the bit coming out. but the bit goes in and the bit comes out again. In what sense is it a copy?
If you fix the second bit to false, the first bit is copied. So don't think of the second bit as part of the input. Think of it as a...
Oh, I see. Now I see what you're saying. Okay, thanks for the explanation.
You're welcome. Oh, yeah, so I'll try to, I'm not sure why, can you see that pointer?
So I can see
I'll
it.
try to use that.
I can see it.
Okay. Okay, so we have this C0, and the C0 goes back to TOEFL, and this was like in the 80s. There was a lot of work on these reversible logic and reversible hardware, reversible kind of circuits, and C0 was one of the most important kind of gates that was discovered at the time. Okay, so now let me, so I'm not going to actually read all of those. I just want to kind of show you that, I mean, once you have the C0 and the idea, then you can build a normal if that goes in, that has functions on both sides, not just on one side. You can iterate C0. So this is an iterated C0 that instead of having one input that is, if that is true, then you do something, then you can have multiple conditional, nested conditionals, if you wish. If the first one is true, and the second one is true, and the third one is true, and so on and so forth, then you do this. So you can do simple kind of generalization of the C0 to build the usual conditionals, iterated conditionals. And once you have that, then you can do some arithmetic. So you can write function that increments Booleans. You can write functions that swap things around. You can do all kinds of things. Now, it is tedious. I mean, certainly, part of the reason I'm showing you is it's not exactly the most intuitive way of programming. But, I mean, this is a calculus. It's a fairly kind of theoretical kind of model, and it's useful for studying kind of properties of the language and so on. And in fact, once you get used to it a little bit, I mean, we've been, quite successful at writing decent-sized programs. And Shao Hong here, my student, wrote some impressive programs in this language. Okay, so just a digression so that you don't think that, this is where you're kind of stuck with this. There is a way, and let me just kind of briefly say, because it's very, very elegant, there is a way to write in a fairly conventional, if you wish, like a functional language like Haskell or something, that has pattern matching. So let me show you, if you have, actually, let's start with C0. So if you have a language with pattern matching, you are used to writing pattern matching on the left and writing some arbitrary expression on the right. So you pattern match here and you do something, whatever here. Now, if you insist that the right-hand side is also a pattern and that every variable that occurs here, then this becomes an isomorphism. And you can prove that, and you can program in this language, and it looks fairly normal. So this is the iterated conditional that I mentioned earlier, and now it's much more readable. So you have patterns on the left, and you have patterns on the right, and you can see that every variable occurring here occurs here, and vice versa. So this is a reversible pattern matching, if you wish, and you can run it both ways, and it's an isomorphism. So we have, some kind of idea on how to make this language that is less cumbersome, but that's not what we're focused on today. Okay, so again, this is, it looks messy, but this is a fairly simple abstract machine. So I'm just showing you a couple of I want to talk about just a couple of the steps. So first, normal kind of abstract machines that we know, they have several registers. So this is a code register, the combinator, the program we're running, the value you're applying it to, and the continuation as a list of frames. Now you can take a configuration that has, let's say, C1, comma C2. So we have a sequencing of combinators. So you say, okay, evaluate C1 and push on the stack that you need to do C2. And when you get to a base case, you have a different kind of state, which is written using these square brackets. And that is a state that says, examine the continuation because we are returning now. So you go to the continuation here. This is a return state. And you see that the continuation has a sequencing operation. And you say, oh, now I need to do C2. So you do C2 and you push C1 on the stack. And this is the only difference from a normal machine, if you wish, because we are trying to be reversible. So we push back the part we have done. So at every point, we have performed part of the computation, and we still have some to do. The usual machine will have the stack, which is what is left to do. But here we also have what we have done so that we can go back and forth. And indeed, if you look at these rules, you can see that every rule can be read from right to left. There's absolutely no problem in reading the rules from right to left or left to right, because every component that is on the left occurs on the right, and you can just do the states backwards. Okay, so sorry. So that was my my point here, is that if you want to read the state backwards, we'll write it this way as with this dagger, but this is the same machine running backwards. Okay, so it's fairly simple to prove that this machine is deterministic in both directions. So if you from one state, there's only one transition to the right, and if you are executing backwards, there's only one transition that is possible to the left. And you define evaluation as usual, as the transitive closure, and you define backwards evaluation that uses the backwards transition, and then you can prove that this is indeed reversible, that if you start from V1, you go forward, you get V2, then you go backwards, you get V1. Okay? So now we will stop a little bit. So now this language, as I said, is a fairly simple language. We can actually write programs that do conditional, do arithmetic, do all kinds of things. And it has all the properties we want as a first-order language. The semantics of this language can be expressed inside a monoidal category. So let me explain these monoidal categories and how they extend. So a monoidal category has a tensor, and it has a unit. And this is supposed to be a generalization of a monoid. So you expect that it's associative, and it has a unit. Okay? And of course, there's coherence conditions, which, I mean, we're not going to talk about too much for these, but we'll talk about them when we get to compact closure. Okay, so we have, in this language, we have plus and times, so we have two monoids. And so there is also a generalization of these monoid categories, which is bimonoidal, when you have two monoids. So you have one monoid for plus and 0, and one for times and 1. Each one of those is, in our case, symmetric, associative. It has a unit. Same one for multiplication. And then we have that multiplication distributes over addition. I mean, the opposite one, 0 times a, also is there because I'm assuming this is symmetric on both sides. And again, there are lots and lots of coherence conditions, but you can fairly, I mean, it's a tedious proof, but you can, it's fairly direct proof to show that the operational semantics using the abstract machine or using an interpreter or something satisfies all of those conditions. Right? So you have all of the conditions to form a bimonoidal category. Okay. So now the interesting thing is it is known that the compact closed categories, you can extend, if you have a symmetric monoidal category and you have essentially a dual for each object, then you can get this compact closed category. And it has some interesting properties we should talk about in a second. So formally, you need for every object, you need a dual object. And then you need these two morphisms, which say that an object and its dual basically you can go back and forth between identity and object and its dual. So the object and dual somehow canceled, and you can get the unit of the monoid, and you can do it in both directions, obviously. So eta, from the unit, you can create an object and its dual, and if you have an object and its dual, you can annihilate them and cancel them to get back the unit. The coherence condition is written this way, but I prefer, and many people prefer, the string diagrams. So this is what it looks like in the string diagrams. So let me read it. So you start with an A, and so look at the text representation and the string diagram. You start with an A, then you, because you have a monoid that has a unit, you can put 1 times A, or the unit times A. So the unit appears. So this is, we're here. You can, using the compact closed category condition, you can change that unit to an object and its dual. So from this unit, you create an object and its dual. And then you reassociate, which is transparent, doesn't show up on the string diagrams, it's implicit. And then you merge this object and its dual to get back identity, and you cancel. Now I put one of them in blue, in black, and one in red, so you can see that it's like something is happening because it's not the same. You created this red A and its dual, and that dual is going to interact with the original A. So something is happening here that you start with the black A, you create a red A and its dual, and then the dual of the red A interacts with your black A and cancels. And now the question is, what is this operationally? I mean, this is, you can write the diagram and you can look at the diagram and it makes sense. And what is it operationally in a language that has, the regular sum and product types that we're looking at? I mean, this is a completely standard programming language, if you wish, with 0, 1, plus, times, could be Haskell, but of course it has reversible combinators. So what are these diagrams? What do they mean operationally? So just to kind of tell you that this is not going to be an obvious thing to answer. With the dual objects, you can do iteration. You can do high-order functions. So it's whatever construction you do will have to be rich enough to be able to define, iteration, high-order functions. And of course, we have two monoids. We have plus and times. So we have two forms of. You have two of these diagrams you have to interpret, not just one. And we have to distinguish between the two constructions. And one of them distributes over the other. So there's a lot of conditions. So we cannot just expect, this to be like a fairly kind of trivial kind of construction. It will be likely quite involved. Okay, so here is the first kind of special case. So now we look at plus. So we're looking at plus, and here's the same diagram, but now I instantiated diagram with the monoid for plus. So there's plus and 0. And now the question is, I imagine this executing operationally. So if I'm executing operationally, I have a little a, a value of type A, and I apply this combinator to it. When I see this plus, this a becomes inject 1 because there's a sum type, and I'm on one side of the sum type. And now I get to this little funny gadget. And if I keep executing to the right, I'm supposed to produce a value of type 0. Of course, there are no values of type 0. So there's nothing I can do except go back, so reverse. So it is a fairly kind of intuitive idea that when you stare at this diagram, that the way to interpret minus a is that execution goes backwards. So you have execution going forward and backward, which we already had in the first language, but now we have first-class control, if you wish. We can embed programs that tell you, I would like to reverse direction and go back, and I would like to reverse again and go back, and so on. So you cannot execute this thing in the forward direction because it has a 0 on the left, and there's no 0, nothing you can provide on the left. And you cannot execute this from the right, so they're asymmetric. You can only execute them from one direction. So the semantics, the only thing that is important here is all of the previous rules you include. They go left and right. You put a little marker. Are you going left? Are you going right? So this marker is the first machine states with a little tag saying go this way or go the other way around. And then when you see one of the compact closure combinators, you reverse. So if I see this V, I go back with a V on the other direction. So if I'm going right, I go left with the opposite direction, and this is the opposite. If I'm going left, I go right. So I already have all of the rules that were reversible, and I'm just now using the rules by using eta and epsilon to tell me which direction I want to go. All of the other combinators maintain direction. These two flipped direction. Okay, so I'll explain this with an example in a minute, but now evaluation is a little bit involved because you can evaluate something from the left or from the right, and you can end up on the left or right. So you have two modes of evaluation, forward and backwards, and so you have 4 possibilities for each evaluation, and I'll show you an example in a minute. Okay, so the same properties, you can prove it's forward deterministic, it's backward deterministic, it always terminates, all of the evaluation forward and backwards are inverses, and you can prove that this is a compact closed category. So the proof is quite involved, but it's all formalized in AGA. So we have good confidence that we can kind of miss a case or anything like this. And so we have all of these meta properties are established that the semantics makes sense. It's all consistent, and we actually do get a compact closed category. Now, once you get a compact closed category, it means there's some notion of high order functions, which I mentioned before. And so we're going to write them this way. And these are essentially, you'll see on the next slide, it's a shorthand for minus A plus B. So minus A plus B is an object that behaves like a function, if you wish. And if you have a combinator from A to B, you can turn it into this little gadget that goes from minus A to plus B. So it takes a demand for A and produces a supply of B. So you can think of a function as demand and supply. You demand an A, you supply a B. So there are lots of examples in the paper that I'm trying to kind of highlight here. So we have the high order kind of functions. We have you can compose them, you can carry them, you can apply them, you can build iteration, you can do all kinds of little things. You can write some very interesting gadgets like this. So you can write a function that takes n minus 1 inputs, and it does something on all inputs, and when it is the minus 1, it does a backtrack. So it backtracks on this particular one. So it now works from n minus 1 to n minus 1. So lots of kind of neat little programming constructions you can do. Okay, so here is like a tiny example. So swap is the very simple negation. It takes inject 1 to inject 2 and inject 2 to inject 1. And if I curry the swap, I get back something instead of B plus B to B plus B, I get one of the b's goes to the other side, becomes a minus b. So I get something like this. It's kind of looks like a strange thing. And when you run it, you can see that you can run it forward. You can provide b equals to b. It did swap. It used to be on the top wire. Now it's on the bottom wire. You can run it backwards. You can do the same thing backwards. You can run from this end, so you can depend a value on the bottom wire. It goes up to the top wire. And you can do the opposite. You can run it backwards, and so on. So all possible forms of executions, forward and backwards. You can value, produce value, think about it as a consumer, consumes a value, produces value, and all combinations would work. And you can change produce to consumers at will. Okay. Yeah, I turned the video.
Yeah, exactly. The audio quality is a bit off, but we're doing our best, I think. It's a bit hard to follow, so maybe speak a bit more slowly until we get over this.
Okay.
If that's possible.
Yeah, it tells me I have a loss of audio. I'm not sure why. Sorry about that. I'll try to speak slower. So the same. We can try to look at the other monoid, which is the multiplicative one with times and 1, and try to see what would that mean. So again, we start with a value of type A, and we would like to see what happens operationally when we execute this program. So we start with an A. When we get to here, we have to produce an A and something of 1 over A. Now, I have no idea what this is so far. And I don't know which A to produce here. I mean, it's a type that has many values. So I don't know exactly what to do at this point. So it doesn't really tell me too much what to do. But what I can infer is when we get here, I have this A that came from the original input. And this value of type 1 over A, which I'm not sure what it is yet, but somehow this pair, so this is a pair that has a value of type A and something of type 1 over A. And these two things have to annihilate and produce a value of type unit, which has no information. So what could that 1 over A be? Well, again, if you think about it a little bit, I mean, there are lots of possible kind of things you can imagine, but it's a fairly intuitive explanation to say that this 1 over A is like a garbage collector. It will deallocate A and get rid of A. And so I have an A and a garbage collector for A, and when they interact, they both disappear, and I get back no information. The problem is, well, there's an easy problem to fix that you have a 0, so you have to fix, cannot include 0 here. The type 0 doesn't mess things up. Okay, so we have to get rid of 0 because otherwise we get some inconsistent kind of behavior. That's not too hard. But the difficult thing is this A that's coming, this A that's coming from the input is, in this particular case, the choice of the caller. Whoever is using that circuit supplies a little a. This A prime is determined by the semantics. I mean, when you see an A, you have to produce something of type A and the garbage collector, and you have no way to synchronize with this A. So A and A prime need to somehow synchronize, and that is quite a challenge. So we have several ideas on how to deal with that. I'll just explain one of them, which is what is the one we're using. It is like basically move everything to have pointed types. So we have like an extra parameter everywhere that is a current value. So there's for every type, there's always a point in focus. And this is the point we use when we are using these combinators. So whenever we see this eta, we have a value in focus, and we use that value to produce those. So if you see the semantics here, if you see an eta and the value v is in focus, you produce this value. And when you see the opposite, you have value in focus, and if you see another value, you throw an exception. If you see the same value, you you garbage collect it. That's not the only way of doing it, but that way is operationally makes sense. We can actually write some interesting programs with it, and it is good enough to produce compact closed categories of pointed types. So that's what we are doing. Now I think I'm running out of time a little bit. So meta theory, all of the theorems that we expect hold. It's deterministic. Evaluation terminates. You have compact closed categories for if you use pointed types everywhere. And just like the other one, now you have high order functions, or things that behave like high order functions. And so this gadget, which will be 1 over v times b, is a space transformer. I like to think about it. It garbage collects the value v to produce the value v. So it is still, it's like the other one. The other one is it consumes an a, produces a b. This one consumes the space for a, produces the space for b. So one of them is a normal kind of backtracking. The other one is a space transformer, if you wish. So now we have the usual things from compact closed categories. You have these high order functions. You have apply, query, composition, and so on. This is the trace operators, which is like the some kind of iteration on using allocation in that case. So all of these things work out. So we have produced an operational semantics for a negative type, which is the dual of plus, and fractional type, which is the dual of times. Each one of them separately is a compact closed category, and each one of them separately can give nice examples. And now we'd like to combine them. This is actually the easy part. So the minus interpreter, the interpreter for the negative types, was taking values forward or backwards, producing all the 4 combinations of supply and demand. The fractional interpreter was allocating, deallocating, but sometimes it throws exceptions if the value is not synchronized. So normal operational semantics of backtracking and exception suggests that you combine them this way, that when you backtrack, you cannot backtrack over an error, right? So the backtracking, the error kind of controls is the stronger of the two monads, if you wish. So we combine them this way. So we have the two interpreters. We make one small change to combine them, and now we can work with both negative and fractional types, allocate, deallocate, backtrack left and right, and do everything that we want. And again, the meta theory all works out in terms of the operator semantics. It's deterministic, it terminates, and evaluation and its inverse are, and the backwards are inverses. We don't have categorical semantics for that kind of combination, and that is an open question exactly what this would look like. I don't really know. So let me just give you like some kind of cute observations. So now, since we have negative, so if you think about it, we had 0, 1 plus times, and now we have minus and inverses, multiplicative inverses. So we are essentially, if you read every type as a natural number or as a number, then these are all rational numbers. So any isomorphism between types, or any identity between rational numbers, will be an isomorphism between types. So we can kind of look at write equations, identities between rational numbers, and try to see what they mean operationally. And they have very interesting computation interpretations. So certainly minus minus a is equal to a, and that is very simple to see actually in the semantics. If you reverse execution twice, you get back the same thing. This one is more kind of interesting. So 1 over a is a. So here 1 over a is a garbage collector. 1 over that is another garbage collector. So the garbage collecting the garbage collector, and so the value basically rematerializes. So you had a value, or you wanted to garbage collect it, and now you garbage collect garbage collector, so the value rematerializes. If you have minus, one component of a pair is a minus, the whole pair is a minus. And again, that this one is, these two are kind of also interesting. So again, on the rational numbers, 1 over AB is 1 over A times 1 over B. So this is a garbage collector for a pair, which is a pair of garbage collectors. This is how to sum fractions. So 1 over A plus 1 over B is A plus B over 1 over AB. And so this is, kind of like a more complicated construction. But you can see that you can, because everything is reversible, you can slice and dice these allocation and deallocation and forward and backwards, and you can do almost anything that preserves the types will have a very interesting computation interpretation. Now we use some of those constructions to build a SAT solver. I'm not going to just explain anything here. It's a fairly complicated construction, but you can actually write a backtracking search that allocates and deallocates wires to search for solutions for a function. So you can actually do some real, in between quotes, programming in that language. Of course, this only runs on very small examples, but I mean, the idea that you can do this kind of backtracking search in this language was quite exciting to us. Okay, so I think I'll have 2 slides to kind of summarize what is happening here and what we are thinking about. So starting from first order reversible language, we added these high order constructions, negative and fractional, made them work together. This is still a simply typed version, if you wish, because everything terminates. So this is a terminating language. Despite this backtracking and allocation, deallocation, everything terminates. To make it universal, we'd like to add recursive types or algebraic data types. So this is like a one extension, and there's work by others who have been doing some of this work and would like to incorporate some of that work that was done by others. And of course, to get a quantum version, we know that the only difference between a classical reversible language and a quantum language is the quantum superpositions. So if you just add quantum superpositions, you get a universal quantum language. And so that's we have done some work on that in a couple of years ago to kind of see how this work out. And we have a small language, a quantum language that does this extension, but without the negative and fractional types. So we'd like to kind of see if we can add all of these things together. The other thing is we also have these diagrams that I've been drawing. I've been drawing some kind of fairly informal diagrams. They're not very precise in the wish. Recently, there was a paper on sheet diagrams that shows how to write these diagrams in a way that is sound and complete. So the string diagrams, there would be actually sheet in this case, like three-dimensional diagrams, are sound and complete. And we also have done with Vikraman and Chauhang some connection between this language and homotopy type theory. So there's also some connections there that we'd like to investigate, connections between these reversible language and kind of topological invariance. So I will stop here, but I'd be happy to, and I apologize for the quality. I'm not sure what was happening. I'll stop here. I'll be happy to take questions if anybody has comments or questions. Yes, please go ahead, Sam.
Can you hear me?
Yes, go ahead.
Maybe you can see me as well. Well, thanks for a very, very nice talk. At the end there, you were mentioning that this is, the analogy with a sort of simply typed lambda calculus, but this is kind of a reversible language. Have you looked at the relative expressiveness? Can you encode simply typed lambda calculus in this language and maybe vice versa via some sort of CPS translation or something?
So we had, okay, so in 2012 in Popple with Roshan James, who started actually, I started this work with him when he was a PhD student. We had, without negative and fractional types, we could translate a first order functional language, like lambda calculus if you wish, but not high order, to this language. And we had a translation and all the relevant meta theorems. So we have the translation without negative and fractional types, and of course we would have to extend that translation for negative and fractional types, but to get like a high order version of the previous result.
Okay.
So we have the translation for the first order language. We don't have it for the high order language yet.
Okay, and I'm sort of interested in, well, is that like a local transformation, or is it in one direction?
Yeah, the translation in the first order case is compositional, yes.
Yeah, but presumably if you try to go the other way, is it possible to go the other way? As in to simulate your language in a simply typed lambda calculus, say by doing a CPS translation or something like that? Isn't the semantics in Agda, for example, essentially doing that? I guess it is, but Agda's a lot more expressive than simply typed lambda calculus. I wonder if it makes essential use of the dependent types or something else.
So we're using dependent types in an essential way for the fractionals, but not for anything else.
Okay.
But so that's why I didn't say it. We have it said it's akin to, and I would like to work on that to make it precise. Yes.
Yeah. Okay. Thanks.
Thank you. Yes. Go ahead, Chris.
Hello, Amr. It's nice to finally see you not in the flesh, then at least live. So you started your talk with taking some motivation from quantum theory, and you extracted the fractional types out of that. My question is about whether you can now sort of go back and add something more to the fractional types to go all the way and make a language for quantum theory. So specifically, I'm thinking about the co-unit for the compact closure that you were talking about as a garbage collector. So in a quantum setting, you can do that sort of garbage collection, but it's like a measurement. It has an outcome. Do you reckon you can label the garbage collection somehow? Have you thought about something like that?
I think this particular, I mean, maybe garbage collection is not the best word when we move to quantum, because this particular, I think, co-unit is more like deallocating an ancilla bit. I guess it is a measurement sentence, but you must know the value anyway. So you copy the value, you allocate something with a, let's say, allocate something with a qubit in the initial state ket 0 or something. You do some computation, you restore it to ket 0, and then you deallocate. So it's that kind of deallocation. In that case, I mean, if the ancilla bit is isolated from the rest, it doesn't really change anything with the rest of the computation. It just deallocates the ancilla. If your ancilla is mixed with the other stuff, then of course it will measure and mess everything up. So in another paper, which didn't mention here, but it's appeared in RC, the reversible computation, we spent some time talking about safe deallocation, how to prove that your ancilla has the right value and it's isolated from the rest of the code. Does that answer the question?
Yes, in some sense, but I think when you say when you were to do something like this would mess it up, you mean you would step outside the framework of reversible computing? Do I understand
no,
that
I meant
correctly?
it will collapse the computation. Like if it's a quantum computation, it will collapse the quantum state.
Okay, maybe I don't understand that well then.
Okay, let's be. We only have done limited work really on how to extend. Okay, okay, let me actually back up. We have an extension from the core language without negative and fractional with quantum superposition. That was a paper in Fossax with Benoit and Juliana. So we know how to add quantum superpositions to the core language. We have done a paper on this fractional types and try to make sure that they correspond to ancilla bits in quantum. But we haven't done the whole combination. So there could be that there's like something like when we combine everything together, you may be right that this might correspond to a measurement. My understanding, or my feeling at least, is if you have a proof that, because you cannot garbage collect an ancilla unless you know its value, and if you have a proof that the value is what you expect, then it should be a safe deallocation. That's my at least feeling at this point. I could be wrong.
Okay, thank you.
Thank you. Yeah, please go ahead. I see more questions.
I guess I would next. Hi. Thanks. Thanks for the talk. It was a really nice talk. I just wanted to ask a couple of things about the what you remarked somewhere in the middle towards the start about pattern matching and how you could have kind of, if you had a valid pattern matching definition from both sides, that gives you something reversible. Does that carry over to the negative and fractional types as well? And what the patterns look like there?
I hope. I don't know. I think we have done some work to extend this idea of reversible pattern matching to high order things. It seems possible, but we don't have like a full construction yet.
Yeah, and I also had a separate question is there a kind of completeness result for this kind of definition? So
The one, the nothing one.
yeah, just on the, I guess, the first order language.
Yes, for that, yes, we have. So that paper with Benoit and Juliana has a. Yes, so it says that all. Yeah, you can write all isomorphisms that way. So it is complete in that sense. Yes. And of course,
Does
it
it
sounds
also
like.
make?
Excuse me?
Yeah. Does it also make sense to basically have arbitrary isomorphisms in the patterns? It sort of feels like there's a natural sort of operational semantics, but then maybe coverage is difficult.
I'm sorry, there's a lot of static. I don't know if it's coming from me or you, but
You might be picking up the wrong microphone from me. Sorry. Does it make sense to have? Yeah, I think it's from me. Does it make sense to have arbitrary isomorphisms in patterns?
in what?
James, if you ask the question in the chat, I will ask it. I will just repeat it.
It's the last word I didn't hear.
Yeah, no, he disconnected. Well, he muted himself. Okay, Robin, go ahead and we can go back to James afterwards.
Okay, can you hear me?
Yep.
Yes.
Yeah, perfect. First of all, Amar, I would like to say thank you for your very nice talk. This was very interesting work.
Thank you.
So I know that you have studied reversible languages with a trace before. And here you start with this compact closed categories sort of from first principles. But when you start with a trace model category, there's construction to sort of get a compact closed category out of it, right? This GOI construction. So had you thought at all about what happens if you take like your reversible language with a trace and then apply this construction to get a compact closed category out of it? Like what happens then?
Yeah. Yeah. I mean, I know that when we started this, I mean, there was like a tension or maybe a puzzle. Which one is more primitive? You know, having the trace or having the high order functions. I think at the time I thought having extending the language to higher order and recursive types seemed more important then, and we did that, and that seemed to be a reasonable kind of language, and some people picked up on that and did some good work. But here I thought maybe that was a premature generalization, and I wanted to see if we can get the very simplest typed terminating high order reversible language, and then we can talk about recursive types and other types and iteration and other things on top of that. So yeah, so there's I have, to answer your question, I don't know exactly what would happen if I would start from a traced language in the first place. I don't know.
Okay, thanks, Robin. So James asks in the chat, does it make sense to include arbitrary isomorphisms, that is, arbitrary programs, in the pattern syntax?
I mean, yes. I mean, we have to be careful, but yes. I mean, this is what we had in that Fosax paper. Is we have arbitrary isomorphisms, and we have I mean, you have to make sure they're terminating. I mean, that was the only thing. When the type system has to guarantee termination, but you can write arbitrary computations. And we, in the example here, I don't know if I can get easily to the slides on this thing. But so I had a let, so I can write let, and kind of do some computations and compose isomorphisms and do arbitrary things. As long as it terminates, it works well. So that
which slide number it is, I can go there in the meanwhile.
Early, I don't know. Probably maybe try 15 or so. I don't know.
Okay. There you go.
Okay. Well, here. So you see here that I mean, you're making your recursive call. You get part of the isomorphism on the sub list, and then you are building a bigger isomorphism on the bigger list. So you just have to make sure that these all terminate. And if they all terminate, then you can, I mean, this all works out.
Okay, James, if you're happy, you can say you're happy.
Maybe I've got the right microphone now. That brings up the question of our recursive types part of the language that you've outlined.
The question was recursive types?
Yeah, how do recursive types fit? But if it's too long, we can take it to gather town, just because we're really overrunning. But if you can give a short answer, then you can do that.
Yeah, I mean, it's just that, I mean, obviously the isomorphisms become partial. I mean, that's the main thing. They become partial isomorphisms, and you can diverge. So you have partial isomorphisms. So technically, they're a bit more involved. But if you terminate, then everything works as we expect, and sometimes you might diverge.